Okay, what we have here is our first resistive inductive series circuit. You guys are going to be doing a handful of these in your homework today, but I'd like to do one as an example for you first, and then hopefully that'll point you guys in the right direction. So what I have here is a pure inductive load and a pure resistive load, and I've already filled in the values that they've given me here, and then we're going to look at a process of elimination. Which values can we solve for? So if you remember before, we would need two values in any one category, and then we would be able to solve for a missing third and fourth value. And here, I see I can already solve for the current, but let's go ahead and do something with our inductive reactance here. Let's convert our inductance into inductive reactance, and we have the formula for that. We've used that frequently enough at this point. So that's going to be 2 pi times the frequency times the inductance. Okay, and if we put that into our calculator, that's going to give us 12 ohms. Okay, so what can we solve for next? Well, based on the information we have, I could either solve for my total impedance or my current. Now, because it's a series circuit and the current is going to be the same across the resistors, inductors, and for the total, I'm going to go ahead and solve for that first. So 15 divided by 5, the voltage divided by the resistance is going to give me 3 amps. And I know that's going to be the same across all of these because this is a series circuit. Okay, so next I can solve for my missing voltage here. So the voltage drop across the inductor would be 3 times 12. So that's going to give me 36 volts across the inductor. Now, no matter what at this point, I'm going to have to start using some AC theory formulas, which is going to be our Pythagorean theorem based on our right triangle trig. Because in a typical DC circuit, I would just be adding up the voltage drops, or I could add up my resistors in a series circuit. But this is AC now, so we're going to have to use Pythagorean theorem to solve for these. So if I'm looking for my total, let's go ahead and solve for the total voltage in the circuit. So based on Pythagorean theorem, if I'm looking for my ET, the voltage total, I'm going to be getting the square root of 15 squared plus 36 squared. And that gives me a total of 39 volts. Now, if I want to find the impedance, I can either divide 39 by 3, which gives me 13. But let's go ahead and practice finding impedance with the AC theory formulas that we're using now. So if I take 5 squared plus 12 squared, that should give me the same answer. So square root of 5 squared plus 12 squared gives me 13. So 13 ohms is my total impedance for this circuit. Now I have all my power categories down here. So I have true power, apparent power, and reactive power. Volt amps, watts, and vars. Now the easiest one for me to input is, I'll go ahead and take the volts and the amps. So the volts and the amps, if I multiply the voltage and the current, that'll go ahead and give me my vars, my watts, and my voltamps in each category. So let's go ahead and work from the left over. So 39 times 3 gives me 117 voltamps. 15 times 3 gives me 45 watts. And 36 times 3 gives me 108 vars. Now, just to check our work, if I wanted to find the voltamps, I should be able to just take the watts squared plus the vars squared and find the square root of that. So let's double check our work. which it does. It gives us 117. Okay, so we've gotten all the easy ones, and this came out pretty clean. We didn't even have any decimal numbers to deal with. But now let's go ahead and look at our power factor and our phase angle. So I can find either one of these at this point, especially since I've already been using Pythagorean theorem. I already know the sides of my triangle. So let's just go ahead and draw the triangle and then pick our values. So I could use any number of them, but the one that's going to work for us every time, and the one you'll see most frequently, is let's go ahead and take our true power and our apparent power. So if I have 45 watts and 117 volt amps, I should be able to find this angle, which is our phase angle, and my power factor. So the power factor would, based on our formulas, just be 45 divided by 117. Our true power divided by our apparent power. And that would give me a power factor of 0.384, now 385. Now typically you're only going to see these in 2 digits. They don't normally carry it out that far. So in this case, let's go ahead and round it up to 0.39. So our power factor is 0.39, or 39. Now with these sides of the triangles, I have my adjacent and my hypotenuse. I could also find that angle very easily using cosine. So cosine of theta would be the adjacent over the hypotenuse, which would be inverse cosine 45 divided by 117, which would give me a phase angle of 67.38 degrees. So that one came out very clean. They won't all be that easy, especially as we start moving into our RLC circuits, which will be our inductive, capacitive, resistive circuits. But this one wasn't too bad. So use this as an example or a template. You thought there was a couple different opportunities for us to solve for our missing information a number of different ways, but we were able to find all our values. If you have any questions, go ahead and give us a call or give me an email, and we'll get back to you as quick as we can. All right, good luck with all the homework. There's not too many problems today, but they do take a little bit longer to solve than some of the ones we've seen earlier in the week. All right, I'll talk to you guys again soon.